Now let us study the periodicity in oxidation state. See, oxidation state is the number of electrons lost or accepted by an atom in any particular species. Now it's a very advanced term which is replacing the valence electrons and valency, which often are, these three terms are very confusing, because this is the actual term which gives us the idea about the number of electrons which are lost or accepted by an atom in any individual species. Always remember, though we have number of elements which shows a fixed oxidation state, or we call it valency, which is also called combining capacity, but simultaneously we have many more elements which are existing in what? The different valencies, or which shows different valencies, or which exist in different oxidation states. That means the same atom of the element in one compound is losing only 2 electrons, whereas in the atom of the same element, maybe in the other molecule is going to lose more 3 or 4 like different number of electrons. So that is why the oxidation state is different in the different species, and that's why we prefer to express the valencies or valence electrons rather in terms of oxidation state. Now what we find is, in case of group 1 elements, like we know alkalis, since all of these are lithium, sodium, potassium, rubidium, cesium and francium. Now since all of these, what we find is, are having general configuration of NS1, they have only one valence electron, so they all show a common oxidation state of +1. So they all exist as unipositive cations, because they easily loses this one electron and they reaches to the previous period's noble gas configuration, due to which they attains high stability. In case of group 2 elements, what we find is, there are alkaline earth metals, beryllium, magnesium, calcium, strontium, barium and radium. All of these are having NS2 general configuration. So they have 2 valence electrons or 2 electrons in their outermost shell. So they all show +2 as their oxidation state, because they all prefer to lose those 2 electrons and reaches to the previous period's noble gas configuration, which gives them extra stability. So these 2 particular groups of the S block doesn't show any variable oxidation states. But let us now move to the group 13, 14, 15, 16 and 17 elements of P block. Now in 13, 14, 15, 16 and in 17. Now in these 5 periods, what we find is, let me first write down the elements here. We have boron, aluminium, gallium, indium, thallium, carbon, silicon, germanium, tin, lead, nitrogen, phosphorus, arsenic, antimony, bismuth, oxygen, sulfur, selenium, tellurium, polonium, fluorine, chlorine, bromine, iodine and astatine. Now in all these cases, what we find is, in group 13, as we know, the configuration is NS2NP1. So how many valence electrons are there? 3. So they all show +3 configuration oxidation state. They all prefer to show +3 oxidation state. In a very similar way, in group 14, the configuration is NS2NP2. So this is the general configuration. So they have total of 4 valence electrons. So they all show +4 oxidation state. Whereas group 15, what we find is, the general configuration is NS2NP3. So they have what? 3 and 2, 5 valence electrons. So they show plus 5 oxidation state. Whereas, of course, from here what we find is they also start accepting electron. They accept electrons, they also shows minus oxidation state, but I will talk about this minus oxidation state after some time. Let me finish off this first. Whereas the 16th group is having Ns2, Np4, 6 valence electrons, so it shows plus 6, whereas group 17 has Ns2, Np5, so 7 electrons, so it shows plus 7 oxidation state. But what we find the most important to note in this case is that other than these plus oxidation state of 3, 4, 5, 6 and 7 respectively, they, especially the elements after group 14. See, if the group 13 elements are showing oxidation state of plus 3, it's fine because they have 3 valence electrons. To attain octet, they have 2 choices, either to lose 3 or to gain 5. So they prefer to lose 3, so that's why they all are existing in the plus 3. When we are moving to group 14, they have plus 4 electrons, so either they can lose all 4 or they can gain 4. So they prefer to share electrons, but that's happening in the atoms of the elements which are smaller in size, whereas down the group what we find is it's the plus 4 state which is more prominent. Whereas in group 15, 16 and 17, they have 5, 6 or 7 valence electrons. So they prefer to accept electron. And that's why, now since to complete octet, the group 15 will be accepting 3 electrons. So what we find is all these are also shows oxidation state of -3. Similarly, oxygen group will show an oxidation state of -2, and the halogen last will show oxidation state of minus because they are deficient of only 1 electron to reach to their complete octet. So that's what we find is it's the negative oxidation state also which is existing simultaneously. But now let us discuss some very important concept like inert pair effect. Now, after discussing these oxidation states, which are like the general oxidation state, which are very similar, which can be easily predicted from the general configurations of the elements which are with the respective group numbers or the respective group general electronic configuration. Let us understand a very important effect or phenomenon which we notice in the case of the p block elements, that's called inert pair effect. Now what we find is after 3D is completely filled, that means after zinc, or what we find is in the p block elements, the elements which are actually belonging to 4th period onwards, like this one, because we know these all are belonging to the second period. These all are belonging to 3rd period, and so from here we have a 4th period. So 4th period elements, 5th period elements, 6th period elements are having their n-1d before them. Now due to this n-1d before them, what we find is that their electrons gets what? Poorly screened. Now once their electrons are poorly screened, what we find that in all these cases what we find is these due to higher penetration of Ns2 electrons as well as poor screening of these valence electrons by the inner n-1d electrons, the ionization energies of these Ns2 electrons becomes very high. It becomes difficult to take out them. That's why what we find is these Ns2 electrons stop participating in the reaction, or it becomes difficult to make them participate in the reaction. Actually, we have to give a lot of energy in order to make them get unpaired. So what we find is in the elements which are coming after 4th period or from the 4th period onwards, elements of the p block, their oxidation state differs by a number 2. That means the gallium, indium and thallium, other than the +3, they also shows +1, +1 and +1. The difference of 2. Why? Because these Ns2 electrons stop participating in the reaction. That's called inert pair effect. In a very similar way, in these 3 cases what we find is they will also show an oxidation state of +2, +2, +2. Arsenic, antimony and bismuth will also show +3, +3 and +3. Selenium, tellurium and polonium will show They will show plus 4, plus 4, plus 4, and maybe plus 2 also, because these two will remain as such. So this difference in the electronic oxidation states also exist, and the reason is poor screening of the ns2 electrons by the inner n-1d electrons, and that's what called in terms of one line or one term called inert pair effect, and that is why this effect is responsible for the tendency of these elements to show two different oxidation states.